Hello everyone, my name is Wesley Gunawan, and I'm an undergraduate researcher at Jalali-Lab. In today's video, I will introduce you to Vivid 2, a low-light enhancement algorithm derived from a physics-based approach. Vivid 2 is part of PhyCV, a groundbreaking library of physics-inspired computer vision algorithms. PhyCV introduces a new approach to computer vision by leveraging physics-inspired algorithms, which draw on natural physical law to create highly efficient, fast, and inherently explainable methods. Traditional handcrafted algorithms rely on empirical rules, but often struggle with complex or dynamic scenes. Meanwhile, modern deep learning algorithms are data-driven and require extensive labeled datasets, making them computationally intensive and unsuitable for resource-limited platforms. Physics-inspired algorithms offer a compelling alternative by combining accuracy with reduced computational and energy costs. This supports power Vivid 2 in PhyCV, making it an ideal solution for edge devices where efficiency are critical. PhyCV is a collection of physics-inspired algorithms developed with the philosophy of reimagining images as spatial pulses and operating on their spatial and spectral physics. The library showcased here includes methods such as PST for detection, PATES for directional edge detection, and Vivid for low-light and color enhancement. All of these techniques share a unifying principle. Rather than relying solely on handcrafted or data-driven feature extraction, they apply physical equation to transform images. PhyCV is an open source on GitHub, where it has garnered a considerable amount of interest from developers, researchers, and industry alike. Because of its compatibility with mobile and edge devices, as well as platforms like NVIDIA Jetson and Raspberry Pi, PhyCV provides a practical route to deploy physics-inspired algorithms with real-time capability. In addition to being useful as a standalone method, these physics-inspired algorithms can be combined with existing machine learning and AI frameworks to deliver more robust and generalizable solutions. One example is using PhyCV as a pre-processing step before feeding images to Amazon Recognition, a paid AI service provided by AWS. By enhancing low-light regions and revealing subtle contours, PhyCV make objects more easily distinguishable, leading to greater accuracy in automated detection and recognition tasks without the need for retraining. On the top half of the slide, you can see the original scene, where the cars and several people are barely detectable. On the bottom, we illustrate how pre-processing with PhyCV significantly improves visibility, allowing Amazon Recognition to identify multiple people as well as the car with higher confidence. This example shows a dark drone video enhanced using Vivid, where previously obscured details become clearly visible in the output. Beyond low-light enhancement, Vivid can also be applied in the saturation channel in HSV color space, transforming undersaturated colors into natural-looking tones while preserving visual fidelity. To understand the evolution of our low-light enhancement algorithm, let me walk you through the progressive optimization shown in this diagram. We began with the original Vivid algorithm, which we first simplified by maintaining a constant phase parameter, creating what we call Vivid light, as detailed in our PhyCV algorithm paper. We then achieved dramatic acceleration by implementing a lookup table approach with Vivid 2. This implementation provides a remarkable computational saving. Consider a 1080p image containing approximately 10 to the 7 pixels. Instead of a computing inverse tangent for 10 to the 7 pixels, we compute an 8-bit lookup table with 256 points. This optimization offers computational advantage of 8100, making Vivid 2 exceptionally efficient while maintaining enhancement quality. The slide shows Vivid Light's equation, which represents our first algorithmic simplification. Taking this optimization further, we developed Vivid 2 by consolidating Vivid Light's two-parameter into a single unified parameter V that ranges from 0 to just under 1. This mathematical consolidation represents a significant advancement in algorithmic efficiency while preserving enhancement quality. As demonstrated in the graph, this transfer function shows Vivid 2's behavior with varying V variable, illustrating how input pixel values are transformed during processing. This example shows DJI Mini 2 SE video recording captured and processed directly on a Google Pixel 8 smartphone, demonstrating remarkable improvement in low-light visibility. Modern smartphones like the Pixel 8 already serve as a visual command centers for photography and FPV drones, receiving live 720p or 1080p video streams for real-time piloting and monitoring. The exceptional performance metrics we've demonstrated for Vivid 2 on mobile processors open an exciting new possibility, integrating this enhancement directly into live video feed. This would allow pilots to see enhanced imagery in real time during the flight operation, dramatically improving visibility in challenging light conditions without adding specialized hardware or significant processing overhead. This table demonstrates Vivid 2 remarkable processing performance across multiple platforms, showcasing its exceptional computational efficiency. The MacBook Pro with M2 chip delivers outstanding performance, maintaining 56 FPS even at extreme resolution exceeding 4K. What's particularly impressive is that ultra-high resolution 4K processing extends beyond desktop computing. The algorithm runs effectively on the Google Pixel 8 smartphone and Raspberry Pi 4B single-board computers. Vivid 2's exceptional lightweight design is perhaps best demonstrated by its performance on the minimalist Raspberry Pi Zero 2W, which still achieved 23 FPS at full 1080p resolution, making it viable for processing on the most constrained hardware platforms. Importantly, the performance data reveals a clear linear relationship between pixel count and processing speed across all platforms. As resolution increases, frame rate decreases proportionally, allowing for predictable performance scaling to any device. To measure Vivid 2's power efficiency, we conducted benchmark on the Raspberry Pi 4 using methodical approach. We first established baseline power consumption by measuring the idle Raspberry Pi voltage and current, calculating power by multiplying voltage and current. Next, we ran Vivid 2 on static image repeatedly at various resolutions while measuring total system power. The algorithm's isolated power consumption was determined by subtracting the idle baseline from these measurements. Our results demonstrate exceptional efficiency across all tested resolutions. At 480p, Vivid 2 consumes only 0.28 watts, while achieving 1317 FPS. Even at 4K resolution, power consumption remains remarkably low at 0.57 watts, while maintaining 65 FPS. The power scaling correlates directly with pixel count. As resolution increases, power consumption rises proportionally. These benchmarks confirm Vivid 2's suitability for power-constrained environments. To summarize, PhyCV is inherently fast because of its simplicity enabled by the use of physics model instead of neural networks. Further acceleration using lookup table makes it possible to run PhyCV on mobile devices in real time. For more information, refer to this reference slide.